All right, so today we're diving into something, I guess you could say it's a little bit meta. We're talking about the philosophy of statistics.
Yeah, meta, for sure. It's like we're taking a step back and asking, what's really going on with all these statistical methods? What do they tell us about the world?
Right. It's easy to get caught up in the number crunching, the formulas, the p-values, but we're going deeper here. We're asking the big philosophical questions behind those numbers.
Exactly. Questions about how we learn from data, what constitutes good evidence, how we should even interpret probability itself. That's what the philosophy of statistics is all about. And especially for our listener, the philosopher out there, this stuff gets really interesting.
Yeah, because, think about it. When we're talking about statistics, we're really talking about the foundations of how we do science. We're talking about how we move from specific observations to general conclusions about the world.
Right. Induction, the nature of evidence, the interpretation of probability, these are all huge philosophical issues that are front and center in the philosophy of statistics.
So in this deep dive, we're going to unpack some of the core ideas and debates in this field. We're going to focus on two major approaches to statistical methods: classical statistics and Bayesian statistics.
And I think you'll find they offer some really different ways of thinking about how we use data to understand the world.
Okay, so let's start with classical statistics. This approach really took shape in the early 20th century, with some big names like Fisher, Wald, and Neyman and Pearson kind of leading the way. What's the defining characteristic of classical statistics?
Well, the central principle of classical statistics is that it focuses exclusively on assigning probabilities to outcomes within what we call the sample space.
Okay, sample space. For those of us who aren't statisticians, can you unpack that a little?
Sure. The sample space is basically just the set of all possible outcomes of an experiment or study.
So if we flip a coin, the sample space is heads or tails.
Exactly. And classical statisticians, they often interpret these probabilities in terms of frequencies.
Frequencies, like how often we'd expect to see a particular outcome if we repeated the experiment many, many times.
Precisely. Now, here's a crucial point, especially for our philosopher friends. Classical statistics, it generally tries to avoid assigning probabilities directly to hypotheses. It focuses on the probabilities of the data given the hypothesis, not the probability of the hypothesis itself.
Okay, so it's not about how likely our theories are. It's about how likely the data are if our theory is true. How does that actually play out in the methods that classical statisticians use?
So, one of the most fundamental tools in classical statistics is hypothesis testing. It's often built around this idea of a null hypothesis.
Right, the null hypothesis. That's the one we're trying to disprove, right?
Yeah, essentially. We assume the null hypothesis is true, and then we look at our data. If the data we've observed would be extremely unlikely to occur if that null hypothesis were actually true, then we might decide to reject it. You know that classic example of the tea tasting lady?
Oh, yeah, the one who can tell whether the milk was poured first or the tea was poured first.
Yeah. Exactly. So in that case, the null hypothesis would be that she can't tell the difference and is just guessing randomly.
So if she gets, 10 cups right in a row,
Yeah.
that's pretty strong evidence against the null hypothesis, right?
Yeah, because if she were just guessing, the probability of getting 10 in a row correct is extremely low. So we might reject the null and say, you know what, she probably does have some special tea tasting ability.
Okay, so it's kind of like a proof by contradiction. We assume something is true, then we see if the evidence clashes with that assumption. But how does this all connect back to that big philosophical question of induction? That whole problem of how we draw general conclusions from specific observations.
Well, I think it connects in the sense that we're using those specific observations, the tea tasting lady getting 10 cups right, to make an inference about a more general claim, right? That she actually has this ability, not just that she got lucky 10 times in a row.
But classical statistics, at least in its stricter forms, it doesn't really frame it as directly proving that she has the ability, does it? It's more about making a decision based on, managing the risk of being wrong.
Yeah, you've hit on a key point there. It's more about controlling error rates in the long run. If we repeat this kind of hypothesis test many, many times, there is a certain probability that we'll incorrectly reject a null hypothesis that's actually true.
So we're not saying she definitely has the ability. We're saying it's so unlikely she'd get these results just by chance that we're willing to risk being wrong and say she probably has the ability.
Right. Now, what about when we want to compare two competing hypotheses, not just test a single null hypothesis?
Yeah, good point. Like maybe we want to compare the hypothesis that she's really good at tasting with the hypothesis that she's only slightly better than chance.
That's where the Neyman-Pearson likelihood ratio test comes in. Instead of just focusing on the null, this approach compares two specific hypotheses, the null and an alternative, and it looks at the ratio of their likelihoods.
Okay, and likelihood, just to be clear, that means how probable the observed data are given each hypothesis.
Precisely. So we look at how much more likely the data are under one hypothesis compared to the other. Based on this ratio, we decide whether to reject the null in favor of the alternative. And this framework also introduces the important concepts of significance and power.
Right, significance and power. I always get those mixed up. Can you remind me?
Sure. Significance is essentially the probability of incorrectly rejecting a true null hypothesis. It's a type I error.
So it's like being fooled by randomness, basically. Seeing a pattern where there isn't one.
Yeah, you could think of it that way. And power is the probability of correctly rejecting a false null hypothesis. So it's 1 minus the probability of a type 2 error, which is failing to reject a false null.
Okay, so power is about not missing a real pattern that's actually there.
Exactly. And Neyman and Pearson, they showed that, under certain conditions, this likelihood ratio test is the most powerful test you can get for a given level of significance.
Gotcha. Now, what if we don't just want to reject or accept hypotheses, but we want to actually estimate a specific value? Like in the tea tasting example, what if we want to estimate how often she can actually tell the difference? What percentage of the time she's right?
That's where estimation comes in, and a key method here is maximum likelihood estimation, or MLE for short.
MLE, yeah. I've heard of that, but I'm a little fuzzy on the details.
So the basic idea is to find the hypothesis often defined by some specific parameter, like the probability of her being correct on any given trial that would make the observed data most probable. So if she gets, say, 8 out of 10 cups right, the MLE for her accuracy would be 80%, because that level of accuracy makes it more likely to observe those results than any other specific accuracy level.
Okay, so it's like finding the best fit, the hypothesis that makes the data we saw the most likely.
Right, but here's the crucial thing to understand. MLE, it doesn't directly give us the probability that the estimated value is the true value. It's not telling us how likely it is that her accuracy is actually 80%. It's just telling us that out of all the possible accuracy levels, 80% is the one that fits the observed data best.
Gotcha. So it's more about finding the most likely explanation for the data, not about the probability of that explanation itself being correct.
Okay.
Okay, and then how do confidence intervals fit into this whole classical picture?
So confidence intervals, they're a way of providing a range of plausible values for a parameter. And they're constructed so that if we were to repeat our entire sampling process many, many times, collect new data, calculate a new confidence interval, each time a certain percentage of those intervals, typically 95%, would contain the true value of the parameter.
Okay, so it's like a range of values that we're reasonably confident contains the true value, based on how often this method captures the true value when we do it over and over again.
Exactly. But here's the philosophical subtlety. That confidence level, it refers to the long-run frequency with which the intervals will capture the true value. It's not about the probability that the specific interval we've calculated from our current data actually contains the true value. It's a tricky distinction.
Yeah, I can see how that could lead to some misinterpretations. It's tempting to think of it as like a 95% chance that the true value is in this interval, but it's not quite that simple, is it?
No, it's not. It's a more nuanced interpretation based on this idea of repeated sampling. Okay, so we've talked about some of the key tools of classical statistics. Hypothesis testing, the likelihood ratio test, estimation, confidence intervals. But you alluded earlier to some philosophical problems with this approach.
Right. Begin to see it's very elegant, it's very mathematically rigorous, but there are some questions about how it connects to our beliefs, to how we actually think about evidence and plausibility. What are some of the main sticking points for philosophers?
One major issue is what we might call the interface with belief. Classical statistics, it gives us p-values, point estimates, confidence intervals, but it's often tough to translate those directly into degrees of belief about the hypotheses.
I see. So like a small p-value tells us the data are unlikely if the null hypothesis is true, but doesn't actually tell us how likely the alternative is.
Yeah.
It doesn't tell us how much we should believe the null is false.
Exactly. And this has led to a lot of confusion and misinterpretation, especially in how people use and interpret p-values, it's easy to slip into thinking that a small p-value means the null is definitely false, but that's not what it's telling us.
Yeah, it's more about the surprise factor of the data, not about the probability of the hypothesis itself.
Right. And then there's Lindley's paradox, which really highlights this disconnect. It shows how classical and Bayesian methods can sometimes lead to totally different conclusions from the same data, which really makes you think about how we go from these objective seeming error rates to our own subjective judgments about what's going on.
Okay, so that's one problem. The difficulty of going from those classical results to actual degrees of belief. What's another philosophical issue people have raised?
Another big one concerns the nature of evidence. Specifically, classical statistical procedures can be sensitive to probabilities of data that we didn't actually observe.
Okay, I'm not sure I follow that. Can you give me an example?
Sure. Think about the issue of optional stopping. Let's say we have two researchers both studying our tea tasting lady. Researcher A, she decides beforehand to do exactly 10 tasting trials. Researcher B, he says, I'm going to keep going until she makes a mistake, but I'll stop after 10 trials at the most. Now imagine both researchers end up with the same data. She gets the first 9 cups right and then makes a mistake on the 10th cup. Sometimes classical statistical tests will give them different results just because they had different plans for when they would stop the experiment, even though the actual data they observed are identical.
Hold on. That doesn't seem right. Why should our conclusions depend on what the researcher was planning to do, as long as they ended up with the same data? It feels like that shouldn't matter for how strong the evidence is.
Yeah, and that intuition aligns with what's called the likelihood principle. This principle states that the impact of the data on different hypotheses should depend only on the likelihood of those hypotheses given the specific data that were observed. Classical statistics, because it sometimes takes into account the probabilities of other possible data sets that could have been observed based on the sampling plan, it actually violates this likelihood principle.
So if we just focus on how well each hypothesis explains the data we actually saw, the two researchers should reach the same conclusions, but classical methods, they sometimes bring in these other considerations.
Exactly. Now, of course, proponents of classical statistics haven't just ignored these criticisms. There have been several attempts to respond to these philosophical challenges and strengthen the foundations of the approach.
I'd like to hear more about those responses. How have people tried to shore up those philosophical foundations?
Well, one line of defense focuses on this idea of strength of evidence, often through the lens of what's called likelihoodism. Thinkers like Hacking and Royal, they argue that the likelihoods themselves, how much more probable the data are under one hypothesis compared to another, are the most direct measure of the strength of the evidence provided by the data.
So it's about how much better one hypothesis explains the data compared to the other, rather than focusing on these long-run error rates.
Right. It's an attempt to give a more direct epistemic interpretation based on the probability of the observed data, given the different hypotheses. Another influential response is the error statistical approach, especially as articulated by Mayo and Spanos. They try to reframe classical procedures not just as mechanical decision rules, but as genuine tools for inference.
So they're saying that those well-defined error probabilities that we get with classical methods, those actually give us a measure of how reliable our inferences are.
Yeah, that's the idea. And they emphasize this concept of a severe test. They say a hypothesis has passed a severe test if the data agree with it, and if there's a very low probability that we would have observed such agreeing data if the hypothesis were actually false.
So it's like saying, look, our hypothesis has survived a test that would have had a good chance of revealing it to be wrong if it was wrong.
Exactly. And it's a way to address that worry about maybe just getting lucky and observing data that seem to support a false idea. And then finally, there have been some attempts to develop more, I guess you could say, theoretical justifications for classical statistics. We have things like Keiberg's idea of evidential probability, which tries to create a formal system for reasoning with statistical evidence. And then there's Fisher's somewhat controversial idea of fiducial probability.
Fiducial probability, yeah.
Yeah.
That one always seemed a little mysterious to me. What's the basic idea there?
So Fisher's goal was to come up with a way to get a probability distribution over the parameters of a model using only the observed data and the assumed statistical model without having to start with any prior probability distribution over those parameters. It's kind of a way to try to get around that whole subjectivity issue that we'll talk about more with Bayesian statistics.
Okay, so it's trying to get something that looks like a probability distribution over the possible values of the thing we're trying to estimate, but without having to inject our own prior beliefs.
Right. And the way he tried to do this often involves using what's called a pivotal quantity, which is this function of both the observed data and the unknown parameter that has a known probability distribution that doesn't depend on the value of the unknown parameter. Then, through a pretty tricky argument, he tried to kind of invert this relationship to get a probability distribution for the parameter itself.
So it's a very clever idea, but it's always been controversial, hasn't it? It seems like it only works in specific cases, and a lot of people have questioned whether it really holds up.
Yeah, you're right. It's definitely limited in its applicability, and there's a lot of debate about whether it's even coherent. But one reason it's interesting from a philosophical standpoint is that it connects to how people often misinterpret confidence intervals.
Right, because classically a confidence interval has this frequentist interpretation based on repeated sampling, but people often want to interpret it as there's a 95% probability that the true value is in this interval.
Exactly. And the fiducial argument, if it worked perfectly, might have provided a way to justify that kind of epistemic interpretation of confidence intervals. But as we said, it's very controversial and not widely accepted.
Okay, so classical statistics has given us a lot of powerful tools for analyzing data, but it comes with some philosophical baggage, especially about its relationship to belief and the nature of evidence. Now let's switch gears and talk about the other big framework, Bayesian statistics. What's the fundamental shift in how Bayesians think about statistical inference?
The core idea of Bayesian statistics is that we can and should use probability to represent our degrees of belief in hypotheses. So unlike classical statistics, which tries to avoid assigning probabilities to hypotheses directly, Bayesians embrace this.
So for Bayesians, it's not just about the probability of the data given the hypothesis, it's about the probability of the hypothesis itself.
Right. And the basic pattern of Bayesian inference is that we start with what's called a prior probability distribution over our hypotheses.
Okay, so that's our initial belief before we see any data.
Exactly. It represents what we believe about the hypotheses before we've looked at the evidence. And then we update these prior beliefs based on the data using Bayes' theorem, and this gives us our posterior probability distribution.
So the data kind of refines our initial beliefs, takes us from our prior to our posterior.
Precisely. And Bayes' theorem, that's the mathematical engine that drives this whole process. Let's go back to our tea tasting lady. A Bayesian would start by assigning some prior probability to the hypothesis that she has this genuine ability, and some prior probability to the hypothesis that she's just guessing. Then, as we observe the data say, she gets 5 cups right in a row. We use Bayes' theorem to update those probabilities.
So if she's getting cups right, the posterior probability that she has the ability will probably go up, right? It'll be higher than her prior probability.
Exactly. Because the data are more consistent with her having the ability. Now, Bayes' theorem can look a bit intimidating if you're not used to it, but the basic idea is pretty straightforward. In a simplified scenario with a finite number of hypotheses, it says that the posterior probability of a hypothesis given the data is proportional to the likelihood of the data given the hypothesis multiplied by the prior probability of the hypothesis. And then we divide that by the overall probability of the data, which is like a normalizing factor to make sure all the probabilities add up to 1.
Okay, so it's basically saying the strength of our updated belief depends on how well the hypothesis explains the data and how much we believed in the hypothesis to begin with.
Yeah, that's a good way to think about it. Now, what about when we're dealing with more complex situations? Like, instead of just 2 hypotheses, what if we have a continuous range of possibilities? Like, we're trying to estimate her accuracy rate, which could be anything from 0 to 100%.
Yeah, how does Bayesian inference work in those cases? It seems a lot trickier than just updating probabilities for a few discrete hypotheses.
So in continuous models, we work with probability density functions instead of just single probabilities. The math gets a little more involved, but the basic idea is the same. We update our prior density based on the likelihood of the data to get a posterior density. And from that posterior density, we can calculate things like Bayesian point estimates for the parameter, which is often like the mean or median of the posterior distribution. And we can also calculate what are called creedal intervals or credibility intervals.
And those credibility intervals, they're kind of like the Bayesian version of confidence intervals.
Yes, but with a crucial difference. Remember how we talked about the tricky interpretation of classical confidence intervals? Well, Bayesian credibility intervals, they can actually be interpreted as the probability that the true parameter value lies within that specific interval, given the data and our prior beliefs. So if we get a 95% credibility interval, we can say there's a 95% probability that the true value is in that interval.
Okay, so that's much more intuitive, right? It's a direct statement about the probability of the parameter being in that range based on the data and our prior beliefs. But I can already see a potential problem here. This whole process seems really reliant on that initial prior belief. What if different researchers start with different priors? Won't they end up with different conclusions, even if they see the same data?
You've hit on one of the biggest challenges for Bayesian statistics, the determination of the prior probability. It's a huge philosophical issue. How do we justify choosing one prior over another?
Yeah, because it seems like if I start with a strong prior belief in something, even if the data kind of point in a different direction, that initial bias might prevent me from updating my belief properly.
That's a legitimate concern, and there have been a lot of different responses to this issue. One perspective is what's sometimes called strict but empirically informed subjectivism, or personalism for short. Thinkers like Savage and DeFinetti were big proponents of this view. They basically embraced the idea that all knowledge and belief is ultimately subjective. So the prior probability distribution just represents your own personal beliefs before you see the data.
So it's like my prior is my prior, and as long as I update it logically using the data, that's fine.
Yeah, that's kind of the gist of it. And DeFinetti had this famous theorem, his representation theorem, that shows how having a prior is mathematically equivalent to making predictions in a consistent way. So any set of consistent betting behaviors can be represented as coming from some underlying prior probability distribution.
So for personalists, that subjectivity isn't a bug, it's a feature.
Yeah, that's one way to put it. But not all Bayesians are comfortable with such a strong embrace of subjectivity.
So how do they try to make Bayesian inference more objective if the whole thing seems to hinge on this potentially subjective prior?
One way is to argue that Bayesian statistics is really a form of probabilistic logic. The idea here is that Bayes' theorem itself is just a mathematical identity. It's not a matter of opinion. And there are arguments, like the Dutch book argument, that suggest if you don't update your beliefs according to Bayes' rule, you can end up with inconsistent beliefs and actually lose money if you were to bet on those beliefs. So even if the initial prior might be subjective, the process of updating using Bayes' theorem is supposed to be the objectively rational way to proceed.
So it's like the rules of logic. The premises might be different, but the rules of inference are objective.
Yeah, that's a common analogy. And then, of course, there's a whole field dedicated to developing what are called objective priors. These are methods for trying to choose priors in a way that minimizes the influence of subjective opinion.
So it's like trying to find a neutral starting point that lets the data speak for themselves.
Exactly. There are all sorts of different approaches, like non-informative priors, maximum entropy priors, Jeffreys priors, reference priors. They all have their own strengths and weaknesses, and there's a lot of debate about which ones are best in different situations.
Sounds complicated. And then on top of all that, we have these more advanced techniques for dealing with the sensitivity to the prior, right?
Yeah.
Like hierarchical Bayesian models and imprecise probabilities.
Yeah, those are ways to try to incorporate our uncertainty about the prior itself into the analysis. But honestly, in a lot of practical applications of Bayesian statistics, people often just use relatively simple priors, often uniform priors, and they rely on the fact that with enough data, the influence of the prior tends to fade away.
So it's like the more data we have, the less it matters where we start.
Yeah, to some extent. Of course, in some cases, the prior can still have an impact, even with a lot of data, so it's always important to be aware of that. Okay, so we've covered a lot of ground here. We've talked about classical statistics, Bayesian statistics, their strengths, their weaknesses, the philosophical challenges they face.
And for our listener, the philosopher out there, what are the key takeaways? What should they be thinking about as they reflect on all this?
I think the fundamental distinction is in how these two approaches view probability and hypotheses. Classical statistics, it's rooted in this frequentist idea of probability as long-run frequencies, and it tries to avoid talking about the probability of hypotheses directly. Bayesian statistics, on the other hand, it's all about using probability to represent degrees of belief, and it gives us this formal mechanism for updating those beliefs in light of evidence.
So choosing between these approaches isn't just a matter of picking the right tool. It reflects some deeper philosophical commitments about what knowledge is, what evidence is, how we should reason under uncertainty.
Exactly. And for a philosopher, thinking about those deep commitments is crucial. Given these fundamental disagreements about how we should even approach statistical inference, what are the implications for other areas of philosophy? How might the statistical framework we're using subtly shape our thinking about other philosophical problems? Like, how might it influence our understanding of confirmation theory or the problem of induction? These are all big questions.
Definitely gives us a lot to chew on. It feels like we've just scratched the surface here.
Yeah, we really have. And the philosophy of statistics is a really active field. There's so much more to explore. We haven't even touched on things like the nature of statistical models themselves, the philosophy of causality, the challenges of measurement. For anyone interested in how we learn from data and make sense of the world, there are tons of fascinating questions out there waiting to be tackled.
Well, that's a great place to leave it. Thanks for taking this deep dive with me.
My pleasure. Always happy to talk philosophy of statistics.